Hi, Y10. I thought the best way to feedback on the wave applications little electromagnetic spectrum test was to record something with you. So here, hopefully you can see on the screen the test going up and down. I'll just go through it with you. So we've got the electromagnetic spectrum, radio, microwaves, infrared, visible, ultraviolet, X-ray, gamma, written in order of increasing. Well, we know gamma have the shortest wavelengths, therefore it must be increasing frequency. Okay. These are parts of the electromagnetic spectrum. Okay, they are so we've got radio right the way through to gamma again, written in order of decreasing. Well, this time we're decreasing, so it's the opposite. It is wavelength. Okay. Which is the correct form of the wave equation? Be careful on this one. We've got wave speed is frequency times wavelength. Some people fell into the trap. The wavelength, frequency and wavelength were in the right order up here, but it was divided by. So just double check that you've got frequency times wavelength. Here for this one, you've got a radio wave. Its wavelength is 1500 meters. The speed is 300 million meters per second. Calculate the frequency. A few mistakes here. Basically, you've got to use this equation here. We know the wave speed. We know the wavelength. So if we divide the wave speed by the wavelength, we get the frequency, and the answer is 200,000. But it also asked you to select the units, which were hertz. Now, one hazard of exposure to infrared radiation, that is literally burning. Okay, it's hot. Heat is transferred through infrared radiation, so you could burn yourself, skin burns. A lot of people put things like cataracts in there. You need to read the question, because that's UV that causes cataracts, infrared burning. One hazard of exposure to ultraviolet. Now there you could have cataract or blindness or damage to the eyes. Skin cancer. If you put cancer, that wasn't sufficient. You needed to say that it was of the skin, because the UV is absorbed in the first layers of skin. It doesn't travel through your body, so it's not going to damage any cells any deeper than the skin. I also allowed, if you put that it was premature aging of the skin. Matching the choice of X-ray with the correct reason. Detecting broken bones, well, that's because the X-rays are absorbed by dense materials. Treating cancer, they kill cells. Yes, you can target unhealthy cells, but it's actually caused because it kills the cells. Detecting sharp objects in baggage, it's absorbed by dense materials again. So detecting broken bones and detecting sharp objects, both absorbed by dense materials. Here, you needed to look at the data, and you were asked, a student suggests that the X-ray dose and the time it would take to get the same dose from background radiation are directly proportional. Use calculations to test this suggestion and state your conclusion. So some people struggled with this one. So we're looking at X-ray dose and the time that it would take to get the same dose from background. So we've got X-ray dose, time it would be taken. So we've got 9 millisieverts, and they say it would take 3 years. 0.5, 2 months, 4, 16 months. So we need to convert our values into something that we can compare. So if we have 0.5 millisieverts in 2 months, that means we've got 0.25 in 1 month. So perhaps we could find out how many millisieverts per month and then compare those. And that's the way to go. Or alternatively calculate how much per year. And what you find is if you do 4 divided by 16, 9 divided by 36, and 0.5 divided by 2, you get 0.25 millisieverts per month. So yes, the answer is, the conclusion is correct. Here we have a question asking us what is happening at point X. Bit of a nasty question here. Because it's actually at point X, it is refraction. The whole process of dispersion, so spreading out all of those different colours in the white light, is happening over all, but at point X, what is happening is refraction of the light. do we put thermometer D here? So we've got thermometer A, B, and C in violet, green, and red. And D there is as a control, okay, so that we can see that the heating effect we're observing is due purely to the light. And here we've got our questions, we've got our answers of how much the temperature has increased in each thermometer. And you can see that we've had more of a heating effect in the red than the green than the violet. So the question was asking you, the conclusion you can make is that red light transfers more thermal energy than violet light. Some of you got yourselves into a bit of confusion over wavelength and frequency. I would stick with wavelength, and just if you remember that we go from radio to gamma rays, and in the middle there we pass through the visible section, but when we go from radio, we go radio, microwave, infrared, means that red must have the longest wavelength, and then we go down to violet having the shortest wavelength. Just helps to remember. Well, it helps me, hopefully it'll help some of you. A similar investigation as with the thermometers was carried out by Sir William Herschel, and he discovered infrared. They want you to suggest how the student could show that the spectrum produced by the glass prism had an infrared region. All I wanted you to do, if I scroll up quickly, was to suggest putting another thermometer just outside the red region, so just beyond thermometer C, and that so that was the first thing, and that you would then see a greater temperature rise at that point. Thermal imaging camera detects infrared radiation, and it says that at night police officers use thermal imaging cameras. Why do they work better at night than during the day? At night, we've not got any infrared radiation from the sun. It's also cooler at night, so the surroundings are cooler. There's more of a contrast in temperature between the criminal and the surroundings, and therefore they can be they'll be shown up more easily. Right, radio and microwaves. Choose two more properties. They both travel at the same speed, or they can be used for communications. Two more properties that are the same for both. So they can both be reflected. They can travel through a vacuum, so that's not right. They can both be diffracted. They don't travel faster in solids than in air. That's sound. They can be used for cooking. I've never managed to cook with a radio. And they can be dispersed. No, dispersion is where you've got lots of wavelengths and you spread them out. So I suppose within radio waves there is a variation, but realistically what the question is looking for here is can be reflected and can be diffracted. Microwaves are used for cooking and communications with satellites. Why must the wavelength of the microwaves be different for each application? Select all the correct reasons. Okay, a lot of people selected the microwaves communication need to travel further than the microwaves for cooking, but this is not correct. Although it's factually correct, they do need to travel further. It's not why the wavelength must be different. Ultimately, the wavelength of the microwaves that we use in our cooking can travel just as far as the microwaves that we use in communications. The problem with the ones for communication is that they've got to go through our atmosphere. So the ones for cooking must be absorbed by water molecules. The ones for communication must not be absorbed by water molecules in the atmosphere. So it's this bottom one and this one here. Okay, those were your two answers. So hopefully that helps. You're now feeling a little more confident in what's going on with the electromagnetic spectrum.